Is the 5th of March, 2026. 5th of March, 2026. The time now is 9:19 a.m. I just came to shower, so this is going to be me talking to myself, and I. So I'm going to get a drink first. We'll get started. Yeah. All the oxide teleporter. I was oxide 14 years. I was oxide 12 years old. The Mensa 11 years old. 11, 12, 13. I've got my PhD. I'm going to Nigeria. My plan is to go to Nigeria, but through the English Channel. So I'm going to France via the English Channel and underground English Channel. From there, I go to fly to Nigeria. That's my plan for that PhD. I'm not going to one way trip because I'm just for my human rights. So we'll college in two, but I'll go to the European Court of Human Rights and demand and request for my operation to complete it, which is like a return of the riches, which is because there'll be human rights violated so many times in kind of the UK. I'm still detained under the Mental Health Act. I'm currently at room number 14, but we go to continue the OBINexus work on ontological research. So I'm the world's first ontological researcher, which is the world around us, here and now, there and then, and when and where, when and whenever. Okay, so that's 3 places of research. So what I'm going to do, so today is the quantum teleporter. So the teleporter of OBINexus is classical. It's like a quantum because Muco OS, M for Mike, U for Mother, C for Charlie, for Oscar, is operating system, user-friendly human rights operating system, physical and digital. In the physical form and digital form, like the compound and the duplex together, and the combination to operating system of building, which is called OBINexus, with Oscar, B for Bravo, I for Indigo, N for November, E for Echo, S for Bella, S for Sarah, S for Sarah. So OBINexus initiative. So primarily this is a teleportation device. So how does it work? So take an orange, and an orange is polar, so it's in polar space. An orange operates in a polar lattice. A polar lattice is basically a polar system. Basically, you got the reflection of a circle of a system. So you got one type of manning distance. Is it Hamming distance? Manning distance. You got Cartesian distance. So you got the some other type of Hamming distance. So basically, you got the Hamming distance. Of positions of two lines of different Hamming distance is a measure of position corresponding to the sum of two equal lengths that differ. So you got Hamming distance, you got Cartesian distance. Take an orange for example. Hamming distance basically has a physical system, but it works in a lattice. So the Hamming distance operates on two strings of vectors of equal length in number of positions. So you can use to model a cube basically. So you can go 0, 0, 0, 0, 0, 1. Which represents where a cube starts and a cube stop, but they are Hamming distances of a Cartesian system. So you get a system of a cube. You can have any shape of a lattice operating on that system, but it still have to be defined by the vector. So 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1. 0, 1, 0 and 0, 0, 1 are the face of the front facing lattice of a square, and you can make this as a rectangle, depending on how you to the equals length. All squares are rectangles, because all squares are rectangles, all rectangles are squares. Not sure, based on the behavior, isometric behavior of the actor, A for alpha, C for Charlie, T for Oscar, O for Orange, R for Romeo, and the trait T for Tango, R for Romeo, A for alpha, I for indigo, T for tango. I'm trying to use the lattice to model to determine the Hamming distance to via the Cartesian distance and the polar distance for polar distance for a polar object. Now, a polar object has a smooth surface, a smooth continuous surface. So we're trying to model continuity of a surface that can rotate. So you have the four types of translation. You have rotation, translation, reflection, reflecting symmetry, and you got other things like dilation, and transformation. So transformation to rotation, rotation object, transformation, rotation is transformation, dilation is not one of them. Transformation, enlargement. So you go forth of enlargement. So enlargement is enlargement. So enlargement of an object, transformation. So you're trying to move an object in Hamming space via a polar object. You look at like something that's round, like an orange, in polar space. Via a symmetry. So a tripolar. So you have the model is this, Nabi. So that's very good. You understand this model now before your quantum system breaks. But if it does not work, guys, then you know that I failed my quantum physics. I'm not gonna have that. So basically, by quantum physics principles, this should work. Because if you have all the space and time, you don't need to hold it anymore while it's operating. So you're going to have space be one dimension and time be another dimension. So you got space and time in a space-time graph, which I don't know how to do, but it's very easy to do, but I don't know how to do them. So, for example, you have three axes of symmetry, three axes reflecting symmetry. So you have your standard extra coordinate. You have your 0, 0, 0, and you have your 0, 1, 0. No, 0, 0, 1. And you have your 0, 1, 0, 0, 1, 1. And this is basically a cube. Now, this cube is a mirror. It's literally a mirror. So it has an orange facing something. We are here. So this cube has a cube. So you can teleport a cube. So if you have a surface here, guys. So if you have a surface here, something in the center of this system. This is an orange, this is basically an orange, and you want it. It's basically a 2D orange, but this 2D shape has to come through. So in space, basically, you have a pi over 4, which is north. Pi over 3, which is east. Pi over 2, which is north, east, south, and pi, which is west. Now, pi is a rotation. So you're gonna use a bearing system to do this. So bearing is basically in 2D. So this was in 2D. So you're gonna have you're gonna have 90 degrees north. You're gonna have a rho, a pitch, and a yaw. So the rho or theta, which is similar to theta, displacement and elevation. So instead of rho, pitch, and yaw, basically this is not obvious. You're gonna have basically everything that has to have a rotation, a displacement, and an elevation based on x, y, z system. But it's basically based on one unit, not one dimensional quantity. So dimensional quantity what's in relation if this is basically a lattice of a lattice operating on 180 degrees, 360 degrees. You have a ratio of 790 degrees over 360 divided by 360, which will give you map to an area of pi r squared, which would be so you can have a area of 360 degrees, which will be mapped to a system of so this will map to some domain and range. So the input domain should be the x star 2. So if you have 100 crystal orange, you have 160 meters. You have so you have 50 centimeters width and height of this cube. And also a pass-through system. This actually is the 50 lattice. It is ruler. This is a square lattice. Now, this is an example I'm giving you. Don't confuse this with the term of function of the system. But good to have this map the space of a reflection, of a projection of the orange on the other side. So you can have a function in time compute ahead of time before you can compute the space. So the space will be so you want the distance to be instantaneous. And how do instantaneous work? It's literally by having the orange mapped to the lattice, but the lattice is a space of historical So the example. So if the orange is on the other side of the lattice, you go to the background layer. Background, which is where the orange is. We go to the midground, which is the lattice stuff. But this is the part of the medium. The typical stuff is part of the medium. Two mediums. Mediums are literally 3D mediums of the earth. So this is square one. So you can extend this lattice to a cube. So this cube is cube is being what we say what property. If it's a square, it will come out as a flat surface, But if you go through a cube like so, because the volume has to be maintained. So the volume equals the base times width and height. So the volume will be two dimensions. So that is basically a two dimensional cube. So that is just to go through two dimensions. So you're gonna do perform all the properties of a lattice of the on. So yeah, we'll see the lattice in space. That's a rotation of property. You're gonna do an enlargement. You're gonna do a translation. You're gonna do enlargement, scalar enlargement, moving it closer. The system has to contain. Wow, this is a fair question time. So just to keep all the measures of the four spaces, enlargement, rotation, and all the ones to teleportation. I know what this lab is a mirror. So you have a four-dimensional method. You got a tesseract. You try to create a tesseract of a tesseract instance, which are how many dimensions. So how many dimensions will give you two. So a tesseract is defined by the two. So a tesseract is really a 4D cube, a cube, 4D cube. So it's a 4D thing, but it's a property of time. It's all of time. So time has to come into space, but it's modelable as a teleportation myself. It can give you three axes of symmetry in three dimensions. So that will project it to the real world. So you can have a tesseract in time that will give you the two axes. So we can do it work in practice. So for four big tesseracts, I'm ready to how many distance of a cube of four big random tesseracts contain 1, 2, 3, 4, 5, 6, 7, 8, 9. So nine, 1, 2, 3, 4, 5, 6. So it has two surfaces and two cuboids and the longitude and the edges contain two bubbles. But we have the four big binary number representing the tesseract. So if you go to the conclusion of the tesseract, how many distance the tesseract. So the difference is in how many distances. So you calculate of what's based on the displacement, rotation, and rotation, displacement of the building. Don't understand. Let me try to run the problem. So rotation is just one problem. So actually, when you say rotation, so rotation is rotation, enlargement, translation, and so basically the rotation, enlargement, and enlargement, rotation, translation, enlargement, and one more. So this is rotation, enlargement, translation, and something. So rotation basically is you see the object. But enlargement means to make it bigger, or scale its dimension. Translation means you move it from point A to point B. But this is what it says. So this is complete over the four axes. There's one more which is translation. Reflection. So reflection will be the alpha. So this is a sequence of reflection. So how you go to example, you're gonna have a rotation of the orange. You have a half rotation of the orange. Then you do a half rotation. So you're gonna go to every so then rotation in the half. Rotation in the half, the two halves of the orange. Two half rotations perform. That's a heterogeneous homogeneous. You have the full orange. You get full rotation in space. And you can put all the properties of the you can measure all the properties of the on one side. So if you can measure the surface, you have the enlargement. The enlargement being so moving up and down if you use a large, you don't need a large one. You're gonna have a translation on the thing. You're gonna a large one you get a double display. You don't need that. You don't need it. So that's a sequence of rotation, translation, and translation. So two half translations, two half enlargement, just back and forth so you're gonna have two reflection of three you're gonna have three reflections of the for the surface. You're gonna have front, back. So you're gonna have let me think. Girl. You're gonna have one half one half rotation. Half rotation. The half reflection will be so you have half reflection. That'll be 3 times 2 is 6. 1/6 will measure rotation. So this is the read right position 4 right 2 reflection. This is so this is how we do the lattice. things are measured also. So the orange is teleportation also understand this is teleportation system. The reason teleport orange is the quantum measurement is as a process. So this is just a measurement of that reflect orange those systems, the focus system. So the reason is also this is this important here. So, it's essentially or but those will be on our side because those will set a policy specific time that is measurable. So it's like a bit of a dirt, before it's collapsed. So it's not just called specific time continuing. Okay. You know what I'm saying? So the lattice is a 4D lattice. It's a square, so it's Tesseract. And this is the square, so it's a square. Basically, the edges of squares are rectangular, keyboard each of them. So you're gonna have something. So when you put the orange in space, you start to take a measure of orange, and then you lattice, and then you start to now use the bridge. The bridge is now the circle of the circle to other. So you look at this is a copy of them. So the thing of this is how to can have between 0, the front axis and the back axis, and then the front keyboard of the process will give you the element step to complete the other side of the matrix. So that's cool. It's a killer process. It's really a killer process. It's a killer process solution. So let me do my work there. So you can see here what I'm talking about. So this is reflection. So you have to have three axes of reflection, which are in half. So you have a straight to find reflection. And so you have they also be triangular, I believe, based on the orange. So cover. So imagine that the orange is cut inside two instead of half concentration type. This is one lattice triangle. And then so you don't have actually so they really have this all standing so orange while we fully self-processing. These are hard to take allocated first before the time. So we can know what the shape of the oranges will get them, what solution will get it before we can self-process. And in time, if you take all the measures of the quantity, the instant teleportation, the instantly, it's like you're pressing a button, the instantaneous, the digital teleportation, present time, the teleportation. So this is a quantum teleporter from the US, for teleporting through and self-process. I think that's what we do. But I know it works. So asking you guys, I really work in theory and practice too. We didn't have the quantum tools to do it.